Are you online? Should. Jinthin, are you there? Is he there, Nat and all, on WebEx?
Yes, someone just had to unmute me, so I'm online.
Oh,
Hey,
okay, Jinthin. Okay, good. So let me introduce you. So the next speaker is Jinthin from Microsoft Azure. He's a principal software engineer at Microsoft. His work is focused on co-design of software and hardware building blocks for high-performance computing platform and performance optimizations. His research interests include high-performance interconnects, protocols, parallel programming models. Before joining Microsoft, he worked at Intel and IBM Research. He has published more than 25 papers in major conferences and journals related to the research areas. And Jinthin actually graduated from the group. So if some of you take a look at the older MVAPICH2X, OpenSMEM, PGAS, so those are the things he designed. Okay, so Adam is saying OHIO. Okay, so so Jinthin, with this introduction, please share your slides and we can get started.
Thanks, Dr. Panda. So you're able to see the screen right now, right?
See the full presentation mode. Yeah.
Okay, sure. How about now?
It has come. Yes.
Oh, perfect. Yeah. Thank you. Thanks. Yeah, thank you, Dr. Panda, for the kind introduction. So it's always a great feeling to come back to OSU, even though virtually, and talk before all of you. So thank you. Thanks for the warm welcome. So today, just wanted to briefly talk about, MVAPICH2 at Azure and also some of the feature and performance highlights on Azure. So let me jump to the, yeah. So, I have kept a simple agenda right this time. So basically, we'll start with a quick overview of Azure, the different HPC SKUs. We'll talk about the latest H series and the latest N series. I'll talk about like what is H, what is N, etc. So basically the HPC and AI training, the two different SKUs. I'll talk about some of the feature highlights and some of the later ones, and then I'll talk about the MVAPICH2 on HPV3. So Dr. Panda in today's keynote talk, he talked about the MVAPICH2 3. So it supports CH4 and then it can support UCX. So we have some good results with that. And we will also talk about MVAPICH2 GDR on the N series VM. We'll talk about the HPC VM image where, you deploy the VM image and basically you're good to go. So, what the different components on that. And I would also want to share some of the performance highlights, including some of the recent work that we did about optimizing all-to-all and then improving the training workload performance, right? So, yeah. So that's a simple overview. Yeah. Was there a question in between or? I thought I heard something. All right. So yeah, a quick overview of the different HPC AI VM series, right? So we have basically two of them, right? One is the traditional H series, which is for the traditional MPI like applications where we have high compute and memory plus high-speed interconnect, right? In our case, that's InfiniBand. So the HB, HC, HPV2, V3, those are the H series. And on the right side, we have the N series, that is the GPU VM. So even N, we can split that into two, one for the visualization and one for the deep learning, right? So, so for this particular talk, I want to focus more on the VM types which have IB, because all of us are interested in high performance communication, right? So, so I will focus about the HPV3 and NDV4. So basically the RDMA supported ones, right? And then just wanted to highlight the fact that, okay, for all the, IB or RDMA enabled VMs, right, we always do one VM per host. So the main philosophy is that, I mean, if at all we have RDMA, right, the intention is to scale out. And if we want to scale out, right, why not start from the node itself, right, and then go from there. And then we expose RDMA using sRAOV, right? So no host interaction or no VM interaction in between. So basically you're getting the hardware directly, right? And I mean, like we use partition keys or P keys to divide traffic, right? So this is one of the latest H series VMs. So unfortunately I'm I'm not able to talk about the upcoming SKU releases, etc. Those are planned to be announced at SC timeframe or immediately after. So I mean, so this is our latest HPV3. So this is with AMD Milan X and IB, I mean HDR200 IB, right? So this is how we configure it, right? I mean, we all are passionate about performance. So we want to make sure that our VMs are, have zero interaction or interference from the, say, host side, and from the network side. So we use something like something called MinRoot, which is a feature in the Windows host. So to partition the processors, right? So here in the diagram, like you can see the teal color, right? So that's the host cores, and so we partition it strictly so that the host cores, the cores which are dedicated to the host are used by the the backend host operating system, and then the rest of the cores are given to the VM. So with this, like there is zero interference from the host side to the VM. So and your all the cores are actually used for the end user workload itself, right? And then like we discussed, it has the ID 200 gigabits per second. We'll show some of the performance highlights, making sure, seeing that, okay, we can see the numbers hitting the close to 200 gigabits per second, etc. Right? So yeah, so this is a simple example of the H series queue, and the next one is the similarly the ND series, right? So this is for the AI training workload. So here also the design is similar, except the fact that it has 8 A100 GPUs and 8 CX6 200 gigabits per second IB, right? And then interconnected using a PCIe switch, and then yeah, so these can talk between, all the GPUs can talk within the node, and then across the node they use IB for communication, right? So here also we can see the host reservation. So 8 cores per NUMA, and so total of 32 cores are dedicated for host. So the VM, when you get the VM, all the cores that are in the VM, which are say the 96 cores, are dedicated for you, right? So there is no interference from the host, etc. And yeah, so this, the N series is typically used for, let's say, the AI or deep learning workloads. Okay, so next I would like to jump to some of the IB or the feature highlights, right? Starting with IB. So, Dr. Pand earlier showed some good results with, say, different IB technologies, etc., right? So, and the good part is that, all the features are available in the Azure itself, right? Because we are exposing the, through sRAOV, so we are not losing any feature, etc., right? So all of them, we are able to support. So, so to start with, say, DCT, hardware offload, you upload the collectives, right? MCAST, SHARP, then dynamic routing. We'll talk about in one of the coming slides about the performance impact, and then the better reliability with Shield, etc., and then tag matching. All those things are supported. So we have both CX5 and CX6 cards. So the latest one, both HPV3 and NDV4 that we talked previously, both of them are using the ConnectX-6, right? So yeah, so wanted to give a quick overview of the different IB features, right? And so this is again GPU direct RDMA, right? So the MVAPICH2 GDR, right? So it supports the GPU direct RDMA. So so GPU direct RDMA is available on the Azure NDV4 also, right? So I mean, basically, I mean, I don't have to explain this, but basically, I mean, you can do RDMA between the host and the GPU, right? So in this case, or I mean, yeah, between the GPUs across the two nodes, right? So so here I have two pictures, like one, the top one is the RDMA from the host memory, and the second one is the GPU memory, right, across the two nodes. And we can see that all the 8 pairs are able to get the peak, say, close to 200 gigabits per second performance, right? So, I mean, just wanted to highlight the fact that, okay, we focus a lot on the performance, and we kind of ensure that, okay, we are actually able to hit that, right? Hit that number. So, and since we are exposing this using, say, I mean, the different IB words, etc., right? So all the, I mean, GDR capable MPA libraries are supported. I mean, including MVAPICH2 GDR, right? So, yeah, SHAR. So, I mean, you all know, right? I mean, the switch-based hierarchical reduction, right? So, I mean, it is supported in on the dedicated NDV4 clusters, not on the public clusters, because I mean, the HDR switches still have some limitation on the switch resources, which can be used for SHAR. So we use it only on the, say, internal or dedicated NDV4 clusters. So, I mean, we did some good work with NVIDIA team to, like, say, UCX-based Sharp AM, Sharp D communication, to making sure, like, those communication is actually secure, etc. So, I mean, so that's being done. And looking at the performance side on the right, so we are able to see, we could hit about the 227 gigabytes per second, like, which is, I mean, you can see that now the bottleneck is now at the NVLink layer, right? So we take out the network from the bottleneck, right? So it's the NVLink limit that we are seeing there. Yeah, finally, and some congestion control numbers, right? So so this is a quick example with a few HPV3 nodes. So I mean, and these are the GPC net numbers, right? So basically, I mean, GPC net benchmark, as you know, right? Say I mean, the first phase is run without congestion, and then you like have a separate group that is causing the congestion, and then you measure the performance, right? Okay, I mean, the congestion factor is like, I mean, how does it behave when there is congestion, right? So the congestion factor 1 means, okay, that's actually, I mean, the network is able to make up for the congestion, and you're getting the good performance, all right? Or basically your performance is not impacted. But so, I mean, here we can see, I mean, this is, I mean, the first two bars are, first two big bars are basically without the congestion, right? So you can see the congestion factor is all over the place. So average, I mean, you can see like a big spike, and the 99th percentile, that's also, I mean, very much impacted. But you can see the with the new average and the new 99, right? That's with congestion control enabled. So you can see, like, there's I mean, most of the pairs are actually actually hitting the congestion factor 1. That means they are able to get the similar numbers as before, right? So yeah, so just wanted to highlight the congestion control. And I mean, this is very critical in the public cluster, right? Because, I mean, unlike a bare metal cluster where you have a view of, okay, what are the different jobs that are being run, right? I mean, you don't have that view in a public cloud cluster, right? So because you only have view into what your VMs are actually doing, right? So in those cases, like, I mean, the congestion control is really valid, right? And really helpful, right? And I also want to highlight the fact that, I mean, we are working closely with the host operating system team to make sure, okay, I mean, the topology is actually exposed to the VM, right? I mean, there are, I mean, MPA libraries, other frameworks, etc., like depend highly on the like system topology. So we, I mean, make sure, I mean, we work closely with them to expose those in a transparent manner to the VM, right? So NUMA distance, the L3, L2, PCIe topology all are exposed to the VM, and also enable the the hardware counters to the VM, right? So basically try to bridge the gap between, say, cloud versus bare metal, right? So basically you want to give a transparent migration, right? So that's the aim here. We're also working closely with NVIDIA partners to say to enable the topology view to the VM. So there's a separate path that we are trying to implement and to get the topology information, etc. So that's the this is actually available in the dedicated cluster. So that's another thing. So those are the like different feature highlights I want to highlight specific for our interest, this group's interest, etc. Right? So with that, I would like to jump to some of the performance highlights with say the MVAPICH2 on the HPV3. So yeah, like Dr. Panda earlier today, right, mentioned about the 3.A alpha release, and then so these are some of the numbers that just compares the point-to-point numbers between the 2371 and the 3.A, right? And 3.A is configured to the build is configured with say libfabric, sorry, not libfabric, the UCX, so CH for UCX, and then we use the UCX 110 version, right? So here we can see the 3.A is actually performing slightly better, right, in terms of latency, 1.7 versus 1.8. But the most important thing is it's actually able to get better throughput also, right? So the bandwidth, both in case of unidirectional and bidirectional, like we are able to hit close to the peak. So so this is actually very great to see, right? So once there are once the tunings are done for the collective operations also, like we'll be able to see this improvement in the application layer also, right? So so that's a good view from here. So it's great to see. Similarly on the intra node side, so these are like across the two sockets, right? So again, we see slight improvement in terms of latency and good improvement on both bandwidth and bidirectional bandwidth, right? So so in this case, like we just compared the 2371, the default version, and then UCX, 3.A with UCX and shared memory, right? So this is, from a performance perspective, this is actually a very good to see, right? So so looking forward to the GA release, etc. So that's a good thing. Unfortunately, due to some time constraints, we couldn't we couldn't get a chance to run like the collective performance, etc. But looking at this, and since collective operations, if these are implemented over the point-to-point, right, we should be able to see those improvement there also, right? So going forward to the GDR, right? So MVAPICH2 GDR on the NDR, right? So this is just showing the benefit of with and without GDR, like the performance improvement. So here also we can see, with GDR, MVAPICH2 is MVAPICH2 GDR is showing getting the expected performance, like we can see the protocol change and the performance improvement there. Similarly, bandwidth, right? It is able to achieve very close to peak, right? It is, I think it's about like 24.5 or so. So it's, close to the peak. So on the bidirectional bandwidth, I think, this might be just a tuning thing. So it was slightly higher than 42, but like we might be missing some configuration or something. So it is slightly lower than peak, but again, like very close to the peak itself. So that's that, and then the HPC VM images, right? So so one of the key things that we want to ensure is that, okay, so when you deploy a VM on Azure, right? So we want to get kind of the same experience on the bare metal system itself. So where you have all the, say, libraries installed, you can just do a module load MPI, your favorite MPI library, and it's there, right? So so that's where the HPC VM images comes in, right? So we specifically tune some of the say libraries, etc., specifically for our queues and say queue specific customizations, say MPI tuning, all those things we put in, and then we publish the images, right? So just like how you do on a bare metal cluster, like you, get the nodes, and then you do a say module load, or you set your LD library path, and then you're good to go, right? So all the say commonly used libraries, right? Say MVAPICH2, other MPI libraries, the Fabric, OpenUCX, and their say custom kernels, all those things are there, including Nickel, DMA Sharp plugin, Sharp D, etc. Right? So, so currently we have different distros like CentOS based and then Ubuntu based HPC AI VM images. So quickly doing a time check, and it's almost 2. So let me quickly try to go over the performance highlights. So these are some of the Nickel numbers. So this is with the all reduced without Sharp, right, on the left side. So we are able to hit, close to the 200 number here. Again, like these are very much in alignment with the bare metal results. And then all to all, right? So again, so once you increase the scale, then now we are limited by the say network limit. As for the smaller scale, it is actually the NV. You're seeing the NV link as the bottleneck here, right? So that's the thing. And then with this just shows the improvement with Sharp, right? So with and without Sharp here. So on the left, so we have one without Sharp. On a really large scale, I think this is probably the largest Sharp job ever. So about with 1,571 nodes. So we are able to. So one thing to note is that on this particular experiment, we had an slightly oversubscription ratio, which was between multiple clusters. So that could be the reason for this drop. I would want to expect a little bit higher here, but here, as you see, like with Sharp, right? So you can see it is again close to the 200 number here. So just want to highlight the fact that okay, the numbers are very much in alignment with the bare metal numbers, right? And quickly, I'll try to wrap up. So this is the Nickel already used bandwidth. So like I mentioned, all our clusters are actually undersubscribed. So so any public cluster you go, like it is under subscription. So this particular experiment is to just trust the fabric, right, and make sure like any pair that you pick, if you run between them, are you able to get the peak number, right? So this is a stress for the fabric, and then stress for the for all the different components, etc. Right? So this is about say 400 or say close to 500 different NDV4. Each with 8 GPUs, 8 IBs, right? And these are trying to do the pairwise Nickel experiment across them, right? So you can see that all the pairs are actually hitting the greater than 185 gigabytes per second number. So this just highlights that okay, the fabric is non-blocking, and it's actually you're actually able to take advantage of the fabric itself, right? So and the last one, so this is some of the one of the recent works that we did, right? So basically, many of you know like MOE, right? A mixture of experts, right? It is one of the models that if you really want to scale out, right, and with more parameters, etc. So and right, for the MOE models, like basically it's all to all is the key algorithm, right? So you have the input, like you split to the multiple experts, and then finally you do another all to all to get that, right? So one of the even though in the previous numbers we saw okay, as the message size increases, you are able to like saturate the network, right? But that was not the case for say smaller message size. So so this particular optimization that we did was to change the all-to-all algorithm, right? We came up with a 2D hierarchical algorithm. So basically, instead of slicing the different chunks, like we you do a strided memory copy to concatenate all of them and then send it out, right? So this design, we were able to get about say 7x improvement for say 256 MB, and about 2x for the 512 MB message sizes. And this design is actually pushed to the an MSQL repository, right? So anyone can take advantage of it, right? So this new algorithm and plus our other framework optimization, MOE model optimization, right? So we were able to get about 40% end-to-end performance. So just showing the numbers here. So and this has actually been merged to the FairSec model also, like our optimization, etc. And this paper talks more about that. So just wanted to highlight that also. So with that, and yeah, sorry, one more last one. So this is another performance highlight of the HPV3, right? So HPV3 in the last year, we upgraded all of them to switch to the Milan-X, which has even higher L3 cache. So we could, so the scaling efficiency, and that's the highlight here, right? So as you increase, right? You basically start to see the impact of higher cache, and then you are getting the super, really nice the scaling efficiency as you go higher, right? So and we have all the different configuration parameters, etc. put in this blog with the different workload numbers, the configuration details, etc. So with that, I think that let me conclude, and I wanted to highlight the fact that supercomputer on cloud, that is getting more and more real, and then you're seeing the top 500 rankings, the graph 500 rankings, where we have made it to the top rankings, right? So and then one of the reasons I wanted to show the all-to-all algorithms, right? So MVAPICH2 has been doing that for a really long time, right? And then like enabling the different say the different supercomputers to like reach that point, right? So those are the kind of optimization that enable the technology and then enables them to climb up the ladder, right? So and to get the high performance and performance, right? So yeah. So with that, let me conclude. I know it's slightly over time, but thank you all for listening patiently, and then I can take any questions.
Thank you, Jinthin. Let's give thanks to him. Any quick questions?
I have a question about the user setups for the MD Milan, the VM with MD Milan processor. So for the bandwidth, memory bandwidth sensitive applications, user may want to change their NUMA per socket settings. So is that changeable in HPV3 or other VM type?
Oh, so you mean the NPS configuration?
Yeah.
Right. Yeah. So currently it is NPS equal to 2 configuration that we are using. So we did quite a lot extensive performance evaluations like NPS equal to 1, 2, or 4, right? So for the different classes of applications, we found NPS2 was the best one that was giving the best performance. And to really answer your question, right? Can you change at runtime? No, you cannot. It is a BIOS level change, right? But the side answer is that this should work best for most of the applications.
I see, but can we change it on the startup time, like in the VM startup code or something like that?
No, so it's actually the BIOS, right?
Yeah.
So if you want to make a change, then you have to reboot the host, right? So yeah, we don't do that, right? So that will be a lot of downtime in between, right? So this is not a good thing. Does that make sense?
Yeah, thanks.
Okay, last question.
Okay, can you go back to the GDR Direct slide?
Yeah.
Yeah. Here you show the bandwidth is sustainable with or without compare, right? What about the latency?
Are you talking about this graph or the other, the one that I showed for all the pairs?
Oh, then maybe the other graph, yes.
Sure. Yeah. So in this graph, we are talking just about the bandwidth, but I mean, and one of the reasons for doing bandwidth here is to say, I mean, most of these training applications are actually bandwidth bound, right? So we wanted to trust the fabric, so that's the main motivation. But I mean, to answer your question, so do we care about latency? Yeah, we do, but not. I mean, the latency matters a lot for our say, I mean, the MPI workloads. I would say for training workloads where say they are the main. I mean, so NGV4 is the main target, right? So that, I mean, we don't carefully look at latency a lot. But having said that, right, I mean, so this latency that we see with the GPU direct RDMA, so we are seeing about, say, about 5 microseconds or so, right? This is all with GPU direct RDMA. And with pure MPA level latency, like we are seeing about, say, 1.7 microseconds, right? So here, so in this case. But this is, I mean, and when you compare this to other clouds, right? I mean, this is actually, I mean, 10x kind of improvement, right? The other ones where you see are like maybe more than 15 microseconds. So yeah. So those are the different things that we consider. Yeah.
Thanks a lot again. So we'll close the your presentation now. Thanks, and we'll switch to the next one. Okay.
Thank you, Dr. Mandaya.
Thank you.